did the side chain reactions of methyl benzene yesterday. Yes. And the side chain was the CH3 side chain, which undergoes oxidation with KMnO4 and free radical substitution. I told you that the ring reactions also occur, which are the electrophilic substitution reactions. And which electrophilic substitution reactions will the benzene ring and methyl benzene undergo? It will undergo halogenation, both chlorination and bromination, mono and trinitration, Friedel-Crafts alkylation, and acylation. Now, I also told you yesterday that if you have X, which is an electron donating group, the incoming group will go on position 2 and 4 or 4. And if it is an electron withdrawing group, it will send the incoming group on position number 3. How do you know something is electron donating or electron withdrawing? If they are saturated, the side chains, if they are saturated, that means if they have all single bonds, we call them electron donating. And if they are unsaturated, we call them electron withdrawing. Yeah. So we can see methyl benzene is a saturated side chain, or it's an electron donating group. And we already know that. I mean, methyl is an alkyl group. And if you remember, electron donating effect of or the inductive effect of electron donating groups or the alkyl groups, do you remember? They used to push their electrons towards the carbon. So they are in any way electron donating group. So now let's see the ring reactions of methyl benzene. So let's see the ring reactions of methyl benzene. So we have electrophilic substitution. So there is electrophilic substitution. Now this will undergo halogenation, both bromination and chlorination. It undergoes mono and trinitration, undergoes acylation, and Friedel-Crafts alkylation. Now, methyl group we know is an electron donating group. Yes. So methyl is an electron donating group. And electron donating groups are also called ring activating groups because they push the electron towards the pi ring. So they are called electron donating groups or ring activating groups. And ring becomes more reactive, yes, because I mean they push the electrons towards the pi ring. So the pi ring becomes more negative and it is more susceptible to electrophilic attack. So we call it electron donating or ring activating group. Why? Because the ring becomes more reactive. Why? Because the electrons are pushed towards the pi ring. So electrons pushed towards the pi ring, making it more negative and making it more susceptible to electrophilic attack. Yes. So that's why it becomes more reactive or active. Yeah. And we know that electron donating groups, they direct the incoming group. So electron donating group directs the incoming group on position 2 and or 4. Yes. So it directs the incoming group on position 2 and or 4. So the incoming group will go on position 2 and or 4. Now, methyl benzene for electrophilic substitution compared to benzene alone requires less stringent conditions or requires less severe conditions. Why? Because you see the ring is reactive. So it requires less severe conditions compared to the reactions of benzene. So compared to the reaction of benzene, the reactions in methyl benzene, they require less severe conditions. Now let's see the first reaction, that is halogenation. Now, if you remember the halogenation of benzene, first thing you had to do was make an electrophile. And what was the reagent? The reagent required was chlorine gas in the presence of a catalyst. So the catalyst or the conditions are AlCl3 catalyst. So you require AlCl3 catalyst. Now let's see the products. So we will get, now you have a methyl benzene, all right? So the incoming group, the Cl, will go on position 2 or 4. So you can get either 2-chloromethyl benzene, or you can get a 4-chloromethyl benzene. So let's see. So we have methyl benzene right here. So to CH3, we add Cl2 in the presence of AlCl3 catalyst. And when you do that, you get two possible products. You get either 2-chloromethyl benzene. Yeah, this right here is 2-chloromethyl benzene. Or you get 4-chloromethyl benzene. So you get 2-chloro or 4-chloromethyl benzene. Clear? And what else will we get? Obviously, the H that has been removed with the Cl will make HCl. So you also get what? HCl. That will give you steamy fumes. Right? Now, these are your two possible products. The first thing that you got to do is generate the electrophile. So how will we generate the electrophile? You have chlorine with AlCl3, which will make AlCl4 minus plus Cl plus. Right here, we've made the electrophile. Now we will have step 1. What will be step 1? The step 1 of electrophilic substitution would be the formation of 4-valent carbocation intermediate. So you have this. So this will make what? A 4-valent carbocation intermediate. Now you can attach it on carbon number 2, the chloro, or you can attach the electrophile on carbon number 4. Now I'm doing it on 2. You can also put it on 4. If you're putting it on 4, then you make the carbocation here, the 4-valent carbocation here. If you're putting it on 2, then you put it here. So this is the chloro, this is the H. And you will show an arrow from the ring to the chloro. Yes, you can show either this going on position 2, or you can show this going on position number 4. Yes. So you can show it on position 2 or on position number 4. Is this clear? So far, so good. Now, in the next step, we will remove the H, expel it H plus. Yeah. So you have in step 2, you will expel the H as H plus. So this H will be expelled as H plus. It will go back in the ring. Yeah. This along with AlCl4 minus, giving you 2-chloromethyl benzene. Or if you were taking 4, that is also fine. So you get 2-chloromethyl benzene, AlCl3 is regenerated, and you get steamy fumes of HCl. So this right here is 2-chloromethyl benzene. And this right here is steamy fumes of HCl. Clear? Now let's see the next type of halogenation. We've seen chlorination. Now let's see bromination in methyl benzene. So let's do bromination. Now the reagent for bromination is bromine liquid. And the condition is you require anhydrous AlBr3. You can also take FeBr3. Also, by the way, the catalyst here is also what? Anhydrous. Because we know in the presence of water, the catalyst will break or hydrolyze. File will be Br plus. Let's see our products. So our products would be 2-bromomethylbenzene and 4-bromomethylbenzene. So you have 2-bromo and you have 4-bromomethylbenzene plus HBr. Now let's see. Let's see the reaction. So you have methylbenzene, to which we are adding Br2 in the presence of AlBr3 catalyst. So you get two possible products. You get either 2-bromomethylbenzene or you get 4-bromomethylbenzene. Clear? Plus HBr. So you either get 2-bromomethylbenzene because methyl is a electron donating group. So 2-bromomethylbenzene or 4-bromomethylbenzene. Now, the mechanism will be the same as that of chlorination, and seen that in benzene as well. So I'm not doing the mechanism again. Now let's see nitration of methylbenzene. So let's see the second electrophilic substitution reaction, nitration. Now this undergoes mononitration and trinitration. Let's see the reagent. So the reagent would be concentrated HNO3 plus H2SO4, which will be the catalyst. This the nitrating mixture. What do we call this? The nitrating mixture. We also use this in benzene, if you remember. Yeah. So this is called what? The nitrating mixture. Right? So you have the nitrating mixture. And this is done at 30 degrees Celsius. If you remember, for benzene, we required 55 degrees Celsius. Yeah. But here you require less than 55 degrees Celsius because methylbenzene is more reactive. So because methylbenzene is more reactive than benzene, so it requires less severe conditions. Clear? Now, what is your electrophile? The electrophile that we have here is NO2 plus. Let's see the overall reaction of mononitration. So let's see the overall reaction of mononitration. Now, where will the nitro group go? On position 2 or 4. So you have methylbenzene right here. To this, we add HNO3 in the presence of H2SO4 catalyst less than 55 degrees Celsius, or you can just say at 30 degrees Celsius. Yeah. What will be your possible products? Your possible products are, you can either get 2-nitromethylbenzene, yes, plus H2O, or you can get 4-nitro-methyl-benzene plus H2O. So you have 2-nitro-methyl-benzene, or you can have 4-nitro-methyl-benzene. Clear? Now, let's see trinitration. Methylbenzene also undergoes trinitration, not dinitration, trinitration. Unlike benzene, which undergoes di, methylbenzene undergoes trinitration. So let's see trinitration. So you have trinitration of methylbenzene. Let's see. Now you have methylbenzene. I'm showing the overall reaction. So we have methylbenzene react with HNO3 in the presence of H2SO4. Now, trinitration occurs at a higher temperature, at 100 degrees Celsius. And now your methylbenzene will direct, the trinitration means 3 nitro groups. So they will go on position 2, on position 4, and position 6. So this becomes what? This 4, 6 tri-nitrobenzene. And you will have how many moles of water? 3 moles of water. And this will be 3HNO3. So this is what you get. And this is called what? 2,4,6 trinitro-methylbenzene. Trinitro-methylbenzene. We also call this what? TNT. What do we call this? TNT, which is used in explosives. So it is used in explosives. Also known as trinitrotoluene, therefore called TNT. Right? So we have TNT being formed here, where the 3 nitro groups will go on position 2, 4, and 6. Clear? Now let me show you the mechanism of mononitration, very similar to what we've previously done. So let's see the mechanism for mononitration. Now the first thing you got to do before the substitution is generate the electrophile. So generate the electrophile. How do we generate the electrophile? You take HNO3 plus H2SO4, the nitrating mixture, will make HSO4 minus plus NO2 plus H3O plus. We've seen this before in benzene. You've made the electrophile. Now you will have your step number 1. Let's see step 1. So you have methylbenzene. Methylbenzene reacting with the nitro group. Now this can go on position 2 or 4. Yeah, I'm sending an carbon number 2. So you have this, you will get a 4-valent carbocation. NO2 goes here on position number 2. Yes. Now let's see step number 2. In step number 2, you will have this 4-valent carbocation. And this will reform the pi ring, and the H will be expelled as H plus. This along with HSO4 minus that was formed when we were making the electrophile will give you 2-nitro-methylbenzene plus H2SO4, which is regenerated. Clear? So this is our product, 2-nitro-methylbenzene, and your catalyst is reformed. Clear? Is this clear? You don't need to know the mechanism. Clear? So it can either go on 2 or 4, the equal chances for the scene. Clear? Now let's start with alkylation. So let's see Friedel-Crafts alkylation. Yeah. Now the alkylation here is going to be slightly different from what we have seen in benzene. So see, it's a little bit of an exception. Therefore, it won't be exactly the benzene, so you have to remember this. Now let's see the reagent. So for alkylation, we take a halogenoalkane. Let's say we want to attach a methyl group. All right. So let's take methane, that is CH3Cl. Yeah. Now this along with AlCl3 catalyst, and this must be anhydrous. Yeah. So the reagent is this, and actually this should come under conditions. So the condition is a catalyst, AlCl3 catalyst, and the electrophile is CH3 plus. Now, let's see. So we have methylbenzene. To this, we want to add another methyl group. So we have CH3Cl. I'm showing the overall reaction in the presence of AlCl3. So the CH3 is right here. Now the incoming CH3 can go on either position number 2 or position number 4. Yes, that's what we've seen. So this is one possible product that you can get 2-methyl, 1,2, dimethyl. So you have on carbon 1 and on carbon 2. On both the carbons, you have methyl groups. So 1,2 dimethyl benzene. Clear? The other possibility, this is one possibility. The second possibility is that you get 4-methyl. It goes on carbon number 4. So 1,4 dimethyl. You 4 dimethyl benzene. Yes. You can also get a third possibility here, is why I told you it's an exception. And it's kind of the other reactions also. You can also get 1,3 dimethyl benzene. Even though 3 is the position for electron withdrawing groups, but here with alkylation of methyl benzene, you can get all 3 products. So all 3 products can be found equally. Yeah, so all 3 can be found. So this is slightly different, where you don't only have on carbon number 2 and 4, but it can also go on carbon number 3. So please remember this exception. All right. Now let's see acylation. Let's see acylation of methyl benzene. So we have Friedel-Crafts acylation. So we have Friedel-Crafts acylation. Let's see. Now this is also slightly different. Okay. So this also has an exception. We will see. Now the reagent for acylation, we need to use a acyl chloride. So let's say you want to attach a ethanoyl group or a 2-carbon acyl chloride. So you will take ethanoyl chloride as the reagent, which is CH3COCl. Clear? Now let's see the condition. So the condition is AlCl3 catalyst. right? And it should obviously be what? Anhydrous. And the electrophile would be what? The electrophile would be CH3CO plus. The charge is on this carbon. Now let's see the overall reaction. So you have CH3 plus CH3COCl in the presence of AlCl3, giving you CH3 here. Now, the acyl group will go on carbon number 4 plus HCl. Now you'll be like, Miss, what about 2? Can it go on 2? No, there is minimum substitution at carbon number 2. Let's see why. So why will there be minimum substitution? Because we said it can go on carbon number 2 and 4. So why is there minimum substitution at position number 2? So why is there minimum substitution? Why does it not go here? Why does it go on carbon number 4? That is because of the size of the electrophile. The size of the electrophile is too large. So you can't fit it on carbon number 2. So it's too large to fit on carbon number 2 because you already have a CH3 here. Fitting this big one right here is difficult. So there is minimum substitution here, is why it goes on position number 4. Is this clear? So minimum substitution on carbon 2 and most of it will go on carbon number 4. Is this clear? So let's go over this. Question number 1. Both ethene and benzene react with bromine, but mechanism of the types of products of the two reactions are different. This is the reaction of ethene with bromine. You know, alkene with bromine undergoes what? Electrophilic addition. Whereas benzene with bromine will undergo what? Electrophilic substitution. Yes. No heat light catalyst needed for ethene. This is your product. And this is your product with benzene. State the type of reaction undergoing in 1 and 2. So 1 is electrophilic addition. And 2 is what? Electrophilic substitution. Yes? Now, moving on, they are asking you to show the mechanism of the intermediate. Need to show the intermediate with ethene and with benzene. So with ethene, you know, it's being bromine being added to ethene, right? So what will be your intermediate? That the Br will go on one of the carbon, the other carbon will become what? A carbocation. Yes. And you will also have a bromo anion, which will then attack this and it will make your product. But you just need to show the intermediate. This is what we have. Then in reaction 2 with benzene, what will be your intermediate? A 4-valent carbocation. It's gone on this carbon right here. So you show it like this. This will be a 4-valent carbocation intermediate. Why do ethene and benzene differ in their reaction with bromine? Because ethene has a pi bond or a double bond, right? So it has a pi bond that can break, and this can undergo what? It can undergo addition reaction. Yeah. Whereas benzene has a pi delocalized pi ring. Yes. So this makes it undergo what? Substitution reaction. And this delocalized pi ring is spread over the 6 carbons. Yeah. Is why this undergoes substitution reaction. Is this clear? So let's see this part. Methylbenzene can react with chlorine under different conditions to give monochloro derivatives F and G. Now, if you see in F, the chloro has attached on the benzene ring. So this must be the ring reaction. So this must be electrophilic substitution of the benzene ring. And in 2, you see the CH3 becomes CH2Cl. So this must be free radical substitution. Yeah. So they're asking you the reaction reagents and conditions for the reaction. So this is a side chain reaction, whereas this is the ring reaction. Now, reaction 1, the reagents are chlorine with AlCl3 anhydrous catalyst. Yeah. And with the ring reaction, we've seen the reagents, and the side chain reaction, you will require chlorine in the presence of UV light for free radical substitution. Then they've given you this. They're saying benzyl benzoate is the constituent of many perfumes, blah, blah, blah. You can't do benzyl benzoate. I mean, you can't get to this part right now. Just this bit right here. So you have methyl benzene. Methyl benzene is becoming, the methyl group is becoming CO2H. So this must be what? Oxidation. And then methyl benzene is becoming something else, which then becomes, instead of the so CH3 is becoming CH2OH. So what do you think we must have here? We must have a CH2Cl here, and then the Cl becomes OH. And what is that reaction? Nucleophilic substitution of halogenoalkanes, which we've done in AS. Yes. So draw the intermediate H above, which we already have. The chloro will become what? The alcohol through substitution. Yes. Then they're asking you, what will be the reagent for reaction 3? So this is undergoing oxidation. So this will be what? Reaction with aqueous KMNO4. Reaction 5. So reaction 5 will be nucleophilic substitution. In place of Cl, you can put OH. So that would be what? Aqueous NaOH plus heat under reflux. This will also be, by the way, in reflux. And then 6, you don't really have to bother with so much. But you can see with C also, you have acid and alcohol. And this is making what? An ester linkage. Yes. Do you see acid and alcohol becoming ester? And this is esterification. So esterification happens in the presence of concentrated sulfuric acid, concentrated H2SO4 plus heat. Yes. State the type of reaction in 3. So we know that is oxidation. State the type of reaction in 5. So we know that is nucleophilic substitution of halogenoalkanes. Is this clear?